welcome to my classroom. In the past lesson, I introduced you to the 4 gas laws: Avogadro, Boyle, Gay-Lussac, and Charles. You might be wondering though, if there's an easier way to memorize them, or even use them in general, and there actually is. This combines our previous laws into a single equation. This is known as the combined gas law. If you pay close attention, you'll see that it simplifies into the basic laws we've discussed previously. For example, Avogadro's law focused on keeping pressure and temperature constant. This leaves volume and number of moles, which is Avogadro's law. You can simplify the combined gas law into all 4 gas laws. For example, if the number of moles and temperature stays constant, you're left with the relationship between pressure and volume, or Boyle's law. The combined gas law allows you to calculate how the variables will change in many different scenarios. For the previous examples, we have always had 2 variables that remain constant. Using the combined gas law, you can even solve scenarios where only one variable is constant or none of them are. Let's work through some examples applying the combined gas law. What is the new volume in milliliters of a balloon, originally 25 liters, whose temperature warms from 15 degrees Celsius to 20 degrees Celsius, while its pressure drops from 759 torr to 700 torr? Just like our previous problems, we first need to identify the constants and changing variables. For this problem, everything is changing except the number of moles of gas. That means PV and T are changing. However, we can rewrite the equation without N since it's constant. Now we need to determine though the values associated with each variable in the combined gas law equation. The initial pressure in this problem is 759 torr. The initial volume is 25 liters. The initial temperature is 15 degrees Celsius. The final pressure is 700 torr. The final volume is what we're looking for. And the final temperature is 20 degrees Celsius. All of the units are consistent, but we need to make sure we convert the temperatures to Kelvin by adding 273 to each. That results in an initial temperature of 288 Kelvin and a final of 293 Kelvin. By substituting these values into the equation, we are left with one unknown. To isolate the unknown, we want to first cross multiply and then divide both sides by 201,600 to get a volume of 27.5778 liters. However, the problem asks for milliliters, thus we need to multiply by 1,000 to get 27,577.8 milliliters. As you can see, I have rounded to the tens place because the problem involved mixed operations, so I round to the least decimal place. Let's try another with less numerical values. A sample of gas at standard temperature and pressure is transferred to a tank twice the original size, where the temperature is increased by 35 Kelvin. What is the pressure of the gas in the new tank? First, again, we need to identify our variables. The only variable held constant is the number of moles of gas, assuming, of course, that 100% of the gas was transferred, which is a safe assumption. That again means that PV and T are changing in this problem. Therefore, we can rearrange the combined gas law as follows. Now we need to determine what values the actual variables will take in the combined gas law. The initial pressure is 1 atmosphere, since the sample is at STP. The volume is a bit trickier though, it never provides an actual value. However, that is okay, you can choose any value. I'm going to choose 1 liter because it's simple. The initial temperature is 273 Kelvin because it's at STP again. The final pressure is what we are looking for. The final volume is just double the value you chose for the initial. In my case, that's 2 liters since I chose 1 liter as the initial point. The final temperature is also a bit tricky. We need to be sure we read the question correctly. It is not saying that the final temperature is 35 Kelvin, but that it's the initial temperature plus 35 Kelvin. Thus, the final temperature is 308 Kelvin. Now we replace the variables in the equation, isolate x, and calculate the pressure to be 0.564 atmospheres. Since the only provided value was 35 Kelvin, and this was only including division and multiplication, the answer would be recorded to 2 significant figures or 0.56 atmospheres. Excellent work! You are on your way to solve just about any gas problem that is thrown at you. Again, make sure to pay close attention to the verbiage used in the question so that you interpret it correctly. Thanks for tuning in, and good luck using the combined gas law.